Welcome to the session on electromotive force and Faraday's laws. Now we are familiar with electrostatic field and magnetostatic field, which are produced by stationary charge and stationary current. Now we are going to deal with an entirely different kind of electric and magnetic field. In the last session, we have seen that electrostatic field and magnetostatic field are functions of position. Now we are going to consider the electric field and magnetic field are functions of position and time. That is a time dependent field, that is we are going to learn about the time dependent fields E and B. Study of time dependent fields is generally known as electrodynamics. So now we are going to discuss the Ohm's law in electrodynamics. So we have a conductor and many charges are inside the conductor, and we have to make the charges in motion. To make the charges move, we have to push the charges. So how fast they move depends upon the amount of push, or we can say that the volume current density J is proportional to the force per unit charge. Here the proportionality constant sigma is known as conductivity of the medium. So here we can see that the conductivity depends upon the material medium. So suppose we have given the same amount of force per unit charge to different material, the amount of current density produced will be different. In our case, the force that drives the charge is electromagnetic, and in the case of an electromagnetic force, F is given by Q into E plus V cross B. So the force per unit charge is E plus V cross B. So we can write the current density J as sigma times E plus V cross B. Here velocity of the charge or the speed with which the charge moves is very small. So we can neglect the second term compared to the first term. So J is equal to sigma E, and it is known as the Ohm's law in electrodynamics. Next we can describe about electromotive force. In order to describe electromotive force, we consider the circuit shown in here. Here a battery is connected to a light, and we can see that all the times the light glows with the same intensity. Naturally we are expecting more effect near the battery and less effect away from the battery. But here we can see that all the times the bulb is glowing with same intensity. That means the driving force is equally communicated all the times. So we can discuss whether the current flowing in is less than the current flowing out, what will happen. So here we can see that the current flowing in is more and current flowing out is less. That means there is some accumulation of charges. So here some charges are accumulated at the knee, and these accumulated charges produce an electric field which is pointing away from the charges, because here positive charge is accumulated at the knee. So the electric field due to positive charge is always pointing away. So here the electric field here in this direction is acting opposite to the direction of current flowing in, and here the direction of electric field and current flowing are in the same direction. That means the electric field produced by the accumulated charge opposes the further current flowing in, but at the same time it enhances the current flowing out. So this process will continue until the current flowing are equal or there is no accumulation of charges. And here we can see that there is some accumulation of positive charge, and how this charge becomes positive. So we know that generally direction of current is taken as the direction opposite to the flow of electron. That means here current is flowing in means electrons are moving out. Suppose 5 electrons moving out, then here we have taken the assumption that current flowing in is more than current flowing out. That means here less number of electrons are flowing out. Suppose here 5 electrons are there and here 3 electrons are there, and both the electrons are moving in this direction. So at the knee the current flowing in is more and current flowing out is less, means here 5 holes are there. When 5 electrons moving from this portion to this, means here there is 5 holes are generated, but from here to here only 3 electrons are coming. That means there are 2 holes. That is the reason why here the accumulated charge is positive. So whenever the current flowing in and current flowing out are not same, an electric field is generated by the accumulated charge, and the electric field should act in such a way to oppose the current flowing in and enhances the current flowing out, and it will make the equilibrium in the knee portion. So here we can see that this is a self-correcting system and it will give the same effect all the times. So whatever be the position of the light or whatever be the length of the wire, we will get the same amount of light all the times. So here we can see that what are the different types of forces involved in driving current through the circuit. The first force is source force Fs, and here it is chemical force, because here we have connected a battery to a bulb and the driving force responsible to move the charge is chemical force, and the second force involved is due to the electrostatic force. So 2 forces are involved in driving the current around the circuit. Then so the total force acting in the circuit is Fs plus E. Now we can see what is the net effect of this force on the loop. In order to find the net effect of force on this loop, we have to integrate the force over that length. So we are finding integral over closed loop F dot dl, that is equal to integral over closed loop Fs dot dl plus integral over closed loop E dot dl. But we have seen that integral over closed loop E dot dl is equal to 0, because E is electrostatic force that is due to the accumulated charge. So integral over closed loop E dot dl equal to 0. So integral over closed loop F dot dl is equal to integral over closed loop Fs dot dl, and it is termed as electromotive force. So E is denoted by the letter epsilon, and we can see that electromotive force is the line integral of force per unit charge. Now we can describe more sources of EMF. Now we have described one source of EMF, that is battery. Now next we can describe the most common source of EMF, and the most common source of EMF is generator. Generator exploits motional EMF. What is motional EMF? The EMF generated when we move a wire to the either direction, then an EMF is generated. That EMF is known as motional EMF, or we can say that motional EMF is the EMF generated because of the motion of the loop to any of the directions. In order to explain this, we can consider this figure. Here in the shaded portion there is a magnetic field acting and is pointing into the page, and we have a loop that is connected to the resistance. So now we move the wire to the right with some speed v. So what happens? Initially this much portion is inside the magnetic field. When we move the wire to the right with some speed v, the portion of the loop inside the magnetic field goes on decreases. And we can see that when we move the wire to the right with some speed v, an EMF is generated, and we can see that a current is flowing. So in order to describe this, we have to find what kind of force is acting the movement of the charges, because here we have not connected this loop to any sources. So here the driving source generate when we move the wire to the right. So what kind of force can act on a moving charge? Because here we move the loop to the right with some speed v, that means the charges are also getting the same speed v. We know that only magnetic force can act on a moving charge, and Fleming's left hand rule gives the direction in which magnetic force is acting. Fleming's left hand rule says that if forefinger points in the direction of magnetic field and middle finger points the direction of current, then thumb will give the direction of force. So here you can find in which direction the magnetic force is acting. So here magnetic field is pointing into the page and wire is moved to the right with some speed. That means forefinger is pointing towards the board and middle finger is pointing in this direction because current charge loop is moved to the right with some speed v. So here we can see that the thumb is pointing in the upward direction. That means when we move the wire to the right with some speed, a magnetic force is generated and the direction of magnetic force is in the upward direction. So because of the magnetic force, the charge in the segment AB experience a force because this segment is only in the direction of magnetic force. So the charge in segment AB starts moving and it constitutes a current flowing in the circuit. And now we can see the expression for EMF. So EMF is given by integral over closed loop F dot dl, where F is the force per unit charge. So in this case the driving force is magnetic force, that is Q V cross B, and here Q, this is the total magnetic force. So force per unit charge means V cross B, and here V and B are perpendicular, so V cross B is equal to VB. So F magnetic dot dl, that is VB dot dl. So this expression becomes integral VB dot dl, and here the magnetic force is acting in the upward direction. So when we project the magnetic force over the length of the loop, only this side, that is over the segment AB, magnetic force and dl are in the same direction. This is magnetic force and this is dl, both are in the same direction, so it will pick the component. In all the other cases, magnetic force is pointing up but dl is in this direction, so F magnetic dot dl is equal to 0 in all other loops. So we will get EMF as VB dot dl, and that dl will contribute only the total length of the segment AB, that is denoted as H. So we will get EMF as VB into H, because V cross B we got it as VB and times dl, that we are integrating over the length AB, that is H. So we got EMF as VB times H. Now we can find the magnetic flux associated with the loop, because the loop is moving to the right with some speed V. So number of lines passing through the surface goes on decreases, because we are moving the loop to the right. So the loop is moving outward to the, when we consider the magnetic field, so we can calculate the number of field lines, number of magnetic field lines passing through the area. So phi is equal to integral B dot dA. And what is the area of this loop? That is width into height. Here it is H is the length and X is the width, or we can write it as, sorry, here it is S. So that is B dot dA means H times S. So that is phi is equal to B into H into S. So here we can see that when we move the wire to the right with some speed V, the flux associated with the loop goes on decreasing, just because we are moving the loop away from the magnetic field. Here magnetic field is acting only in this much region. So the rate of change of flux, that is d phi by dt, is equal to Bh into ds by dt. Here we have not taken h because h is always constant, but this length is changing when we move the right loop to the right with some velocity. So Bh into ds by dt. So ds by dt is the rate of change of distance, that is velocity. Here we are showing a negative sign just because when time increases, the length of the portion inside the loop goes on decreases. That means time and the distance covered are inversely proportional. In order to show that inverse proportionality, we show this negative sign. So from here it is clear that we got an expression E, that is equal to VBH, and here we got an expression d phi by dt is equal to minus bhv. So, here we can see that the right hand side is same apart from a negative sign. So, from this we are equating the left side, that is EMF is equal to minus d phi by dt, that is known as Flex rule for motional EMF, that is EMF generated is equal to negative rate of change of flux associated with a loop. Now, we are going to generalize the situation using Faraday's laws. So, in 1831 Faraday reported a series of experiments. Here we can see that 3 experiment situations are shown in here. In all the situations, this shaded portion shows the magnetic field region, and the magnetic field is pointing into the page, and here we have a loop that is connected to the resistance, and the purpose of resistance is to measure the current flowing through that loop. So, in the first experiment we can see that the loop is moving to the right with some speed v. Then we have seen that a current is flowing through the circuit. In the second experiment we moved the magnet to the left with some velocity v, and in this case also we have seen a current is flowing through the circuit. In third experiment we kept the magnet and the loop are at rest, but we change the strength of the magnetic field. In this situation also we have seen that current is flowing through the circuit. So, if we compare the first and second situation, we can see that the only difference is the relative motion between magnet and the loop, that is in first situation we moved the loop to the right with some speed, but in the second situation we moved the magnet to the left with some velocity v. In the context of special theory of relativity it has to be so, but at the time of Faraday there was no idea about relativity. So, we can see that the first situation, that is the loop is moving to the right with some speed v, is exactly same as the magnet is moved to the left with some velocity v in the towards left. In the context of relativity it is so, and we can see that the first situation, that is magnet moved to the right with some velocity v, is exactly same as motional EMF. And we have already seen that the force responsible for driving a current in the circuit is magnetic force. Next we can describe the second situation, that is loop is at rest and the magnet is moved to the left with some velocity v. So, in this case what kind of force is responsible to generate a current in the circuit? Of course, we know that it is not electrostatic, because electrostatic field cannot generate an EMF. Already we have seen that EMF is equal to integral over closed loop E dot dl. If it is electrostatic, the force per unit charge should be E. So, integral over closed loop E dot dl, that is 0 for a static electric field, static E. So, it is not due to electrostatic field, then this is not due to a magnetic force also, because here the loop is at rest. We know that magnetic force exerts only on a moving charge. So, it is not due to magnetic force or electrostatic force, here a current is generated. Then what kind of force can exert a charge at rest? Only electric field. So, this is an entirely new kind of field that is driving the charges in the circuit. Here we can see that when we move the magnet to the left with some velocity, the magnetic field associated with the loop goes on decreasing. That means this new kind of electric field associated with the change in magnetic field. So, this change in magnetic field induces an electric field, and that electric field is responsible for driving charge in the circuit. Faraday's law says that the EMF generated in the second situation, that is when the magnet is moved to the left with some velocity v, and EMF is generated, and the generated EMF is perfectly due to a change in flux, that is minus d phi by dt. And the main important thing is that here the driving force responsible to produce a current in the circuit is electric, and this electric field is associated with a change in magnetic field. So, here we have written this EMF, that is the line integral of force per unit charge integrated over a length. So, EMF is integral over closed loop F dot dl, and here F is the force per unit charge, and here in the case of electric force, F is given by Q E. So, F is equal to F by Q, that is equal to E. That is the reason why here we have written this EMF as integral over closed loop E dot dl, that is equal to the negative rate of change of flux, that is known as Faraday's laws in integral form. So, from the second experiment it is clear that an EMF is generated when the magnetic field associated with the loop changes. So, an electric field is generated with the change in magnetic field. Now, we can rewrite this integral form of Faraday's law in terms of differential form. For that, we are applying Stokes theorem. So, integral over closed loop E dot dl is equal to integral over closed loop del cross E dot dA. So, that is equal to, we are substituting on the right side, that is minus d by dt of phi. Instead of phi, we are substituting B dot dA, because phi is the magnetic flux associated with the loop. So, that is equal to minus, we are taking this d by dt inside because time and space are entirely independent. So, we can take the differentiation with respect to time inside. So, this right side becomes minus integral over closed loop del B by del T dot dA. So, here we can see that the integration is with respect to area on both sides. So, we can equate the integrands on both sides. So, we will get del cross E is equal to minus del B by del T, that is known as Faraday's law in differential form. So, now we have described the second experiment, that is what kind of force is responsible to generate a current when we move the magnet to the left with some speed, but at the same time the loop remains stationary. So, Faraday's law says that an EMF is generated whenever the flux associated with it changes. So, in the third experiment we can say that the strength of the magnet goes on changes. In that case also an EMF is generated because flux associated with the loop changes. So, Faraday's law says that an EMF is generated whenever the flux associated with the loop changes. Whatever be the reason for the change of flux, an EMF should be generated, because in the second experiment the magnet is moving to the left and there is a change in flux associated with the loop. But in the third experiment the magnet and the loop are at stationary, but we have changed the strength of the magnetic field. In both the situations there is some reasons to change the flux, because flux is given by phi, that is surface integral B dot dA. So, it may be due to the change in magnetic field or it may be due to the change in area. So, whatever be the cause of change in flux, an EMF will be generated and the induced EMF will be given by the negative rate of change of flux, that is Faraday's laws. Now, we can see how can we find the direction in which the induced EMF will flow. So, for that we can see this. So, in this case we can see that when we move the wire, the loop to the right with some speed v, the flux associated with the loop goes on decreases. So, here in order to give the direction in which the EMF is induced, we can use Lenz's law. It states that induced current will flow in such a direction that the flux it produces tend to cancel the effect. That means, the induced EMF will be produced in such a direction to oppose the change in flux. When we move the wire to the right with some speed v, the flux associated with the loop decreases because the area inside the magnetic field region goes on decreases when we move the loop to the right. So, according to Lenz's law, an EMF will be induced in such a direction to oppose the change in flux. So, here the flux is decreasing, that means the field due to the induced current will be in such a direction to oppose the decrease in flux. So, here we can see that if the current is flowing in clockwise direction, then the magnetic field induced will be in the towards the board, that means it should oppose the decrease in flux. So, when we move the wire to the right with some speed v, and EMF is induced in the clockwise direction. The reverse will happen if we move the loop to the left with some velocity v, because in that situation if we move the loop to the left with some velocity v, the flux associated with the loop increases because more area are inside the field. So, in that situation the EMF induced in the loop should be in such a direction to oppose the increase in flux. That means the current should flow in anti-clockwise direction, then the magnetic field should pointing away. So, it should oppose the increase in flux. So, depending upon the direction of movement of loop, the current will be induced in the loop, and from Lenz's law we can generally find the direction in which the induced EMF flows through that circuit. Let me conclude with this. In this session we have seen electromotive force, motional EMF and Faraday EMF. Motional EMF is one which is produced in a loop when we move the wire to the right with some speed, or due to the movement of wire and EMF is generated in the loop, or we can say that in the case of motional EMF the driving force is magnetic force. But in the case of Faraday EMF, an EMF is generated when we move the magnet to the left, or due to the motion of magnet an EMF is induced in the circuit. But in that situation the force responsible for driving the charge through the circuit is electrical. So, the driving force responsible for producing the motion of the charge in these two situations are entirely independent. In one situation it is due to magnetic force that happens in motional EMF, but in the case of Faraday EMF the EMF is induced due to an electric field generated in the loop, and this electric field is associated with the changing magnetic field. So, that is the important concept given by Faraday, that is a changing magnetic field induces an electric field, and this electric field is known as Faraday's electric field. Go through the textbook and get a feel about the Faraday's laws and try to do the problems in the textbook and get a feel about all these laws. Bye for now and have a nice time.